Hey there, I'm Alejandro, and welcome back for day 143 of me doing the NeetCode 150 challenge. So today we're doing our very first LeetCode Hard Advanced Grasp problem, and so without further ado, let's get straight into it. Okay, so today we get LeetCode Hard from 332 Reconstruct Itinerary. So two disclaimers before I start. One is me and my friend Osmani are about to get dinner, and so I need to do this problem as fast as possible. He's worried that I can't fit this in under an hour. I'm just trying to say I'm going to try to do this problem in 30 minutes. Second disclaimer, Reconstruct Itinerary. This problem is not one that I'm unfamiliar with. I don't think I've ever, so I've never actually solved this problem before, but in my daily LeetCode challenge, I actually solved something that was a strictly harder version of this problem. In fact, I remember that problem. I don't know Reconstruct algorithm, but essentially the hard part of that problem was like you didn't know what node to start with, and so you had to treat it like I think it was relevant to like Eulerian circuits, and you need to use like Reconstruct algorithm to find like or how to do something with Eulerian circuits and so on, and eventually like figure out what node to start and then do something with the problem. I remember whether it was in the video or after the video, I ended up looking at the editorial. And in there it said, here's an easier version of this problem. It was Reconstruct Itinerary. And I remember seeing like, oh, okay, Reconstruct Itinerary is the problem for this, except it's the same problem, but you could have started with every node, which removed the entirely super difficult part of that problem. So I forgot what this problem actually is. I just remember that it's that this is a strictly easier version of that LeetCode Hard I did in my daily LeetCode challenge, where the difference was that in that problem you had to use like Reconstruct algorithm to figure out what node to start from. And in this problem it was one of those where it's like either the start node is given to you or you could start from any node. But nevertheless, those are two disclaimers, and I'm going to try to do this problem as quickly as I possibly can, and if I can't do it in 30 minutes, I'll probably take a break and come back whenever I can do it. So without further ado, let's get right into the problem. You're given a list of airline tickets where tickets of I is equal to from I to I represent the departure and arrival airports of one flight. Reconstruct the itinerary in order sorry, and return it. All of the tickets belong to a man who departs from JFK. Okay, so start node is given to you basically. Thus, the itinerary must begin with JFK. If there are multiple valid itineraries, you should return the itinerary that has the smallest lexical order when read as a single string. For example, the itinerary JFK LGA has a smaller lexical order than JFK LGB. And so what do we want? We want the smaller or the, so smallest lexical order. Okay, cool. You may assume that all the tickets form at least one valid itinerary. You must use all the tickets once and only once. Okay, just from this, I have no idea what this problem is asking. Okay, so here it says... okay, so here, so what is this like tickets? Okay, so tickets are edges. So MUC to LHR, yep. JFK to MUC, yep. SFO to SJC, yep. LHR to SFO. Okay, sure. 1, 2, 3, 4 edges. 1, 2, 3, 4 edges. Okay. And here it says JFK, MUC, LHR, SFO, SJC. Okay, well that's just the BFS. Here's like all the edges. Here it wants JFK, Atlanta. Oh, JFK, SFO, Atlanta, SFO. So what, is it like you always... Wait, let me read this problem. Okay, one time. All the tickets belong to a man who departs from JFK. Thus, the itinerary must begin with JFK. There are multiple valid itineraries. You should return the itinerary that has the smallest... So it's like what? This guy wants to use every single ticket? Once and only once. Must use all the tickets once and only once. I see. So you need to do a full itinerary. I remember this problem was like not that difficult. Reading it makes it seem difficult. Is it just like can I get away with like a BFS and it's like from my neighbors I always pick whichever one has the smallest lexicographical order? That's what I'm thinking of, right? Let's try that. I need some water, but okay, no worries. Adjacency list is equal to, here we'll do a default dict of what? List, here we'll say, okay, for, from, okay, we'll just say u, v, and tickets. These are directed edges, right? So here we'll say adjacency list of, here we actually will do, collections.deck, if anything. Just because we'll probably want to pop from the left when we, okay, can we sort a collections.deck? Let me open my terminal. Okay, this is from a previous problem. That's actually for the daily today. Let me do this, Python 3. If I do import collections, here I do collections.deck with, we'll do a couple numbers here. We'll do this. There we go. Here we'll say, you know what, q is equal to this, q.sort, is that a valid thing? Sorted q. Yeah, okay. So not really. Okay. Sorry. My throat. Okay, no worries. Adjacency list of u, we'll do dot append v. Right? Or if anything, we can use a heap, right? Yeah. Yeah, you know what? Here we'll do heap q dot heap push into adjacency list of u, and here we'll push in v, right? Here, that way we can do printf string adjacency list equals. Here we can just do list. Okay, so here there's only one node per option. Yeah, so here I can just do itinerary is equal to this. Q is equal to collections.deck starting from JFK. While length of Q is greater than 0, here we'll say airport is equal to q.popleft. And here we won't have a visited set, right? But that's the point. Here we'll do itinerary.append airport. Right, this is our solution. So we'll start off with JFK like we're doing. Here we'll say we only want to pop one neighbor, right? Ooh. So maybe we should do current node. Yeah, if anything, for now we can use a queue, but I think we only need one node at a time, right? Because here I'm going to do something like q.append if length of adjacency list of airport equals 0, then break. Is greater than 0, then we'll do next airport is equal to, yeah, airport is equal to JFK. Here we can just do while true equal to 0. Here we'll break, otherwise we'll say loop invariant airport is equal to heap q dot heap pop from adjacency list of airports. And return itinerary. Is it something as simple as this? Okay, we have it accepted. Let's submit. Wrong answer. Okay, let's see what's wrong with this. Here, let me print a string, the adjacency list. So here what happens. Airport is equal to JFK. We append that to itinerary. Length of adjacency list of airport. No. So we put in cool. But cool has no neighbors. So yeah, so this is what I don't understand. You go to cool. Oh, I see. You can go to JFK, JFK to NRT, NRT to JFK, JFK to cool. I see, so you need to end up using all the tickets once, and there's at least one valid itinerary. I don't remember why I remember this problem being so simple. It was like, oh, you could just do a BFS. Why did I remember this being so simple? I remember this was just a much easier version of another problem we did. And ticket set length is only up to 300. Oh, this is a 332. Do you do like some mega DFS? You need to use up all the edges once. So maybe you do it based off who has the most amount of neighbors. Or maybe you use a queue. Right, the point is you go to call, and call has no neighbors, so really you want to go to NRT first. It's almost like you want to branch out into different possibilities. Yeah. You want to go in terms of like the one that has the most inwards edges at a time. So maybe a heap is good, but the in degrees also matter. This is fine. In fact, this is actually quite inefficient. We could just append and then heapify. Yeah, so really worst case we do adjacency list of u.append v, and then for node in adjacency list of node dot sort printf string adjacency list equals 1, 2. Yeah. Heap q dot heapify. You see a list of you. Yeah. JFK, if they're multiple, yeah, I think that's what I'm really focused on. Really, I should just first of all find a valid itinerary. At least one valid itinerary must be. Yeah, I spoke to Cockily for this problem. Okay, this is a little harder than I expected. I don't remember why I thought this problem was so easy before. It's like all you needed to do was like a simple BFS or DFS or something simple, and you were there. Or no, I guess this problem is like traveling through a Eulerian circuit, where it's like you want to go through all the edges. It's just that like you don't have to use like Huel's algorithm or something maybe, because it's like you know where you have to start from, and that was the hard part. Yeah, I wanna try something like I wanna keep track of all the nodes in degrees. In degrees is equal to default ticked event. U comma v in tickets. Yeah, here this will be easy actually. We'll do this. Define adjacency list. Yeah, but for now we don't need to do this. Here we'll just do in degrees of v plus or equal to 1. printf string adjacency list equals printf string equals JFK1. Oh yeah, this was like a property of our learning circuits, right? Like, ooh, wow. Everything must be like 1 or 2s or whatever. It's like pick the one that is smallest in terms of lexicographical ordering, right? But do I really want their nodes and their indegrees? I mean, for now we can do something simple. Neighbors equals adjacency list of nodes. I mean, we could do some things like quadratically, right? Like, that's not a problem. If anything, yeah, here we'll just do Q is equal to collections dot deck of, or here really we'll say node is equal to JFK. While true, we'll say, here we'll just call it res. Res of append node. Next node is equal to none. Neighbors equals adjacency list of node. Oh, we should be able to have an O of 1 remove, right? Oh well. Yeah. So here we'll just do a set. Here we'll just do .add v. Oh yeah, it is thundering and stuff in Seattle.
Dude, it's raining.
Yeah, it's hard.
We should have gotten you.
Yeah, I'm sorry, bro. I'm sorry. Low-key, this is harder than I thought.
I'll cook.
The what?
Ooh,
Oh, we'll figure something out. Don't worry. I love thunder. We should watch Ted or something.
Okay.
When you hear lightning, grab your thunder buddy and say these magic words. La 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 la. You guys don't know that. We're innocent.
Oh, I have chicken tenders.
Oh,
Yes.
banger. Yes, from Costco.
And we have the oikos.
Yes, you deserve. Okay, as the append node, yeah. Yeah, it's not gonna be a trivial problem, but that's okay. It's NeetCode hard. It doesn't have to be trivial. As append node, neighbor is equal to adjacency list node. Yeah, for now I should try to get something inefficient and working, not something not working. Where's the append node? Neighbor is equal to adjacency list of nodes. Equals none. Nay, comma degree. None. Float of negative infinity. Best nay. Best degree. Neighbors. We'll say in degree of nay. If degree walrus operator is less than min degree, best nay equals nay, min degree equals degree. Loop invariant. Node is equal to best nay. If length of neighbors equals 0, then break. Assert length of itinerary of res equals length of tickets, right? Something like that at least. 1, 2, 3, 4. 1, 2, 3, 4, 5. Plus 1. And here we'll just say break. Really, we could just return, but yeah. Temp res. Best nay. Node is equal to best nay. Yeah, and here we'll say first of all, adjacency list of node dot remove best neighbor in degree of best neighbor minus or equal to 1, which is why I'm worried about using a min cube, and then node is equal to best neighbor. Okay, what happens if I run something like this? Well, that doesn't make any sense. Neighbors is equal to adjacency list of node. Oh, none. We want the one with the highest degree. So here we want max degree. Max degree is less than that. And here we'll say max degree is equal to degree. Printf string res equals. SFO Atlanta. Shoot. In degree of node, right? Or no? Best degree is equal to and oh, I see. This is lexicographically smaller. We'll say max degree is less than that, and best nay less than nay, and neighbors of 0. In degree of neighbors of 0. Here we'll say max degree is less than that, and Yeah. Yeah, so we want to do degree is equal to in degree of neighbor if this is less than degree, or max degree equals degree nay less than best nay lexicographically, something like that. Okay, it's annoying. How do I get a single element from a set? Let's do help set. Add clear copy difference, discard intersection, there's disjoint pop. Remove symmetric Yeah, so I can't just get a random element, right? I'd have to pop and put it back. That's annoying. First nay is equal to first.pop. First nay. Neighbors dot add first nay. There we go. Just do one. Okay, so here we still have a wrong solution. And neighbor is less than best nay, right? So it's smaller lexicographically. Here drew JFK Atlanta. SFO Atlanta. Yeah, so for okay, if anything, what I might do is here, you know what, we'll do this. We'll just do if max degree is less than degree. Right? We'll keep things simple. Right, but here we'll just do this. For node in adjacency list of node dot sort. It might need to be reverse or the other way, like shoot. Okay. Sorted neighbors. What the heck? Reverse equals true. This is annoying. No, we definitely don't want reverse equals true, but okay. It's just quite bizarre. I guess I should be grabbing the one with the, that's the thing, do you grab the one with the smallest degree? How do you know which one to grab next? I guess it's like you try the best one and then otherwise you backtrack. Right? Maybe you sort things by lexicographical order and you just return the very first time you find a full solution, right? Is this just like a backtrack? I mean, if this was just a backtrack problem, it'd be backtracking. Why is this so complicated? I remember this problem being very, very, very easy. By the way, Osman, are you making the nuggets?
Yeah.
Oh yeah, okay, okay, nice. You showered already, right? Or
No, not yet.
not yet? Mm.
I'm doing NeetCode as well.
Nice. Which problem are you doing?
I just did a group of anagrams. I'm doing top K frequent numbers.
I see.
Again, these ones are pretty easy.
No, you're just good, bro. That's nice. Dude, that's some tough stuff right there. Okay. So why do I remember this problem being so trivial? JFK, I'm gonna want to go to Atlanta. I'm gonna want to go back to JFK so we can do this and this. Is it because there was some sort of greed? Okay, we can try with backtracking. -1. Nodes for nay and sorted neighbors. We'll do list dot pop. There we go. Itinerary dot append backtrack yield from backtrack itinerary dot pop insert equals nay. And no.add nay. See? First solution is JFK Atlanta, JFK SFO, Atlanta SFO. Well, that's correct. Like return backtrack of 0 basically. You'll say for res and backtrack, turn res, turn the first. And backtrack, right, return the first. Okay, submit this. Is this just as simple as backtracking? There's no way, right? Backtracking is way too slow. Okay, but at least we come up with a valid. Oh, it's not even valid, eh? Sheesh. Really? What? 11. I see. So what's the maximum length? I don't remember why I remember finding this problem so simple. It's like, okay, either everything has an integer of 1 or has like an integer of 2, right? Can something have an integer of 4? Right, let's just make sure that we print that. Printf string integer. I think the integers are going to matter a lot here. So some of these guys have 3. So it's like, yeah, here the expected solution was JFK, so then to anu, then to eze, then to accent, into Tia, into Anu, into JFK, into Tia, into Anu, Tia, into JFK, jeez. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 3, 4, 6, 7, 10. 11. 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7. That doesn't make any sense. Oh, Return none. There is no solution, it's saying? Oh, it's because of the rest of the code. Interesting. It's saying there's no solutions that were found. Well, that should make more sense. Here maybe we do itinerary.pop. Yeah. Interesting. Longest path of that cost. So we want a path that is of this length.
Right, I did this one too.
Yield airport for airport and itinerary. Return. The point is he just wants to go through all the flights. Like this sort of neighbors is equal to 0. If there's no neighbors for it to get to, then return. Otherwise, for each and every single one of its neighbors, it really is like, you know, you can return, you can, or something like that. It's like something with either integrity or, you know, lexicographical smallness. Do I just populate them all at a time? Right, like I want to see, it's like, okay, out of all my neighbors, can I do it with the one that's lexicographically smallest? If so, then great. Right? Printf string very equals. So here, what do we want for? We want JFK anu eze aksa tia anu JFK tia
Can I distract you for a sec?
Sure.
This meme is too good.
What? Oh, okay. Bro, okay, I see. Nice. Do we just never get to there again? Tia JFK. That one didn't work. I knew it's an accent. Went all the way back here. so weird. JFK new is X at the end. New JFK. Yeah, we try adding JFK. Yeah, showing adjacency list equals. It's gonna be really hard. Right. For Tia, it's got JFK. But JFK we're saying has no more neighbors? Hold up here. Just hold up a sec. Does JFK go to like Anu twice or something? Like, are all the tickets unique or no? Wait, is there a duplicate in here? Assert length of tickets equals length of set of tickets. I don't wanna be lazy here. What? Oh. Tuple ticket, and tickets. Ah, there is a duplicate, isn't there? Adjacency list of U is equal to dict of dict. Here I want to say import from collections, import default dict. D is equal to default dict event. Or was default dict of lambda default dict event. df4 of this should give me 0. Yeah, I see. Of lambda default dict event. U of v plus or equal to 1. At this point, I should just make an adjacency matrix, but okay, whatever. Assert this guy square equal to 0. He will do continue. Otherwise, he will say this guy minus or equal to 1. This guy plus or equal to 1. Okay, so now we have a working solution here. But it's probably too slow, right? Or, oh, okay, print. Okay, we're doing good. Hashtag print. Yeah, I know that when I did this problem the first time, I didn't really have access to, or I didn't know about yield returning, I'm pretty sure. Or actually, no, I probably did because I was definitely doing the daily LeetCode challenge and after I started work. Okay, 7 MS on that one. Let's submit. Let's go! Bada bing, bada boom. We have a slow solution, but at least I was able to do it. Phew! Okay. Wow. Wow. Yeah. Neighbor dict. Adjacency list of node. Neighbors. Neighbors. Here we can replace this with neighbor. Dict. Adjacency list of nodes. Adjacency list of nodes. That's crazy that there can be duplicate edges. Here we can just do itinerary.pop. Here we'll say return false. Return true. To end all backtrack calls. Here we'll just do return res. We'll just say if this. Return true. Just to make things a little bit faster. Well then. Hi boy. Okay, we'll just keep the yield froms. Yep, this is fine. Well, that might be why. Here we'll call this neighbor dict. No. Oh. Well, this would be obvious. That's called backtrack. Nice. And now we do this. Beautiful. Beauty. Here we'll just say self.res. Can just become res. Okay. So this should just make things, okay, well, never mind, because now it just cannot identify it. So that's fine. It's just constant work. Oh, nice. Okay, let's submit. Okay, so yeah, it doesn't seem like we're much faster anyways. Jeez, okay. So, I mean, if that's the case, we can just keep some of the... yeah. Yeah. I mean, like, yeah, I don't know. I'm not that proud of the solution. Obviously here we don't even need n degrees. And yeah, there's probably a better way than to do default dict or default dict, but oh well. Pop. Backtrack, return self.res. There we go. Beauty, let's just submit. There we go. Okay, so we have a slow solution, but at least we have a solution. Might not be the intended way to go about this at all, but you know, at least I was able to do it. That is really what I care mostly about for this challenge. So there we go, bada bing, bada boom. So nevertheless, as always, in my videos, I do a quick recap of ISO solve problems. So this one, essentially, Reconstruct Itinerary. This is a problem where we start at airport JFK, and essentially, what this problem really is you're given a graph of basically nodes that are airports and edges that are like, you know, flights between those airports, I suppose. And essentially, you want to use up every single edge. These edges are called tickets, right? Tickets from one airport to another. And you want to use up every single ticket. Now, the person, what is his name? Like Bob or something? Or just a man. Let's call this man Bob. Bob wants to go through every single ticket. And he doesn't want to waste a single ticket. Bob paid really, really expensive prices for these tickets. He wants to use every single one of these tickets. But Bob has OCD. And with his OCD, Bob wants to go through the airports, not just in any order, but if he can, in order of lexicographically smallest. So for example, if Bob has the option between going to Atlanta and Zimbabwe, he'd rather go to Atlanta because A is lexicographically smaller than Z from Zimbabwe, right? So not only does he want to use up all the tickets, out of all the possible ways that he could use up all the tickets, he wants to make sure that he does so in whatever is the lexicographically smallest ordering possible, right? Starting from JFK. And so the way that I solve this problem is really in a very cheeky way. I would not be surprised if this is not at all the way that you're supposed to solve this problem, right? Because it's an advanced graph problem, and I just put some backtracking where I just come up with the very first solution. But then nevertheless, I'll show how I was able to do it. So essentially here I build a very weird adjacency list where instead of having like, you know, a list of nodes, I essentially have a dictionary of dictionaries of frequencies. So essentially it's like in this tickets, Bob might actually have duplicate tickets. And so in order to account for that, I need to keep track like, okay, for every single edge UV, what is the frequency of that edge UV, right? So here's like I have a dictionary of dictionaries, right? A default dict that returns default dicts of ints, right? So it's like for every single UV in tickets, I'll be, okay, adjacency list, let's look at use neighbors, right? Which will be a dictionary of, you know, where the keys are use neighbors and the values are the frequency of that, you know, edge u to v. So, okay, in this dictionary of use neighbors, let's go to key with value v, right, from uv, and let's augment the number of times this occurs by 1, right? So out of all of use neighbors, whatever neighbor v is, right, we're going to augment the frequency of, you know, of times that v is use neighbors by 1, right? Because there could be duplicate edges and tickets, which will matter. And here, essentially, I just slap backtracking for this problem. So here I start from itinerary, which is JFK. Here I have self.res, which is what I'm going to return. And here I just have a backtrack, which I'm going to make a singular call to. And the point about this backtrack is I'm not going to exhaust all possible solutions. As soon as I find one possible solution, I'm going to set self.res to that solution. And I'm going to return true. And that way, every single subsequent backtracking call, I say like, okay, backtrack, return true, and so on, so it's like, it'll kill all the backtracking calls. So that way, it's like whatever the first solution I come up with will be the solution I immediately return, right? Once I have a solution for my backtracking, I stop there, I will return that and everything. So it's like, it's not super inefficient, right? The very first time I find a solution, I'm done, right? But it is still backtracking, so it's like, it could take forever. Here's going to be my end condition, right? The point is we want to use up every single ticket, right? So if there's 4 tickets, there's going to be 5 airports, right? Because it's going to be starting at JFK, right? And then you're going to use 4 more tickets, which means you're going to go 1 place, 2 place, 3 place, 4 more places, right? So you start from JFK over here, and you're going to do plus 4 more places. So there's going to be length of tickets plus 1 total places you want to be, starting with JFK. So it's like, okay, itinerary is the current thing that we're building through our backtracking. So if the length of the current itinerary is equal to the length of tickets plus 1, that means we must have used up every single ticket. So let's set a result. Res will be equal to, okay, a copy of itinerary, just in case, because it's like, I don't want to deal, maybe I could just do itinerary just because I will not change it anymore. Right, and there we go, right? In this case, usually I'm scared because in backtracking, it's like, since it's the same reference, it'll end up being like, the empty list every single time. But here, since I'm early exiting the very first time that I find a solution, I don't have to do anything of this such, right? So here I could actually return this, and then just return itinerary, and this will work just fine, right? Beauty, right? So we can submit something like this. And nice, 12 ms and so on. So at least we're a little bit closer, but yeah, you can tell the standard deviation is here, so there's probably something more efficient. But the way that I do this is like, okay, this will be my base condition. And so here it's like a return true, and then every single other backtrack call will check like, okay, backtrack, return true. That's like, just stop, all exiting, right? So here what we're gonna do is like, okay, since we're not at our end condition, we need to still visit the next node instead of our trip over and over and over, right? So we're gonna say, okay, whatever's the last node in our itinerary is the node that we're going from, right? And so here it's like, okay, let's do adjacency list of node. Remember, this will be a dictionary where the keys are the neighbors and the frequency is the number of times you can go to that neighbor from our current node, right? So here we'll have our neighbor dict, which is adjacency list of node. And here I'm going to sort the neighbors, right? If I sort a dictionary, it'll just basically sort the keys. So here I'm going to sort them. And the reason this is important is because, again, we want the lexicographically smallest solution. So what I'm going to try to do here is basically, it's like, okay, out of all my neighbors, I'm going to sort them in lexicographical order. And I'm going to tell myself, okay, what I want is this. I'm going to try the one that is smallest lexicographically ordering. I'm going to add it, try to backtrack from there. If that returns a solution, great, I'm going to take that one, right? Otherwise, I'm going to come all the way back here and be like, okay, this is my lexicographically smallest next neighbor, but if I choose this one, I cannot reach a solution. So let me go to my second, lexicographically smallest neighbor, try to backtrack and see if I'm able to come up to a solution. If not, come back and go to my third lexicographically smallest neighbor and try to go from there, do a solution, blah, 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 right? But it's kind of inefficient because we'll end up sorting all of the neighbor dict every single time. But again, I was trying to come up with a solution that works, not one that was necessarily efficient. As long as I'm able to solve the LeetCode hard, I am happy because it just gets me one step further through this challenge. But once I'm done explaining, I might as well investigate, how did NeetCode do it and so on, and how I could have made it a bit better. But nevertheless, it's like, okay, we'll sort the neighbors by lexicographical ordering, and then we'll loop through them in that exact lexicographical order, and we'll do exactly what it's talking about, right? Here I was just doing this just because I'm cheeky, but otherwise it's like, okay, if neighbor dict of nay, wait, what is this? Oh, yeah. Yeah, this I can just completely get rid of. What am I doing? Oh, no. This is the frequencies. Yeah. Yep. So yeah, if a neighbor, if the frequency of the node to a neighbor is 0, right? Then here, what I really should do is something like this. No, it's fine. It's just, it would save me some loops, right? So here's just like, here I could do this, adjacency list of node, adjacency list. frac for node comma frac in adjacency list dot items if frac greater than 0, right? So here I could do something like this, and this would still work, right? The adjacency list of node nay. Oh yeah, because here I'm not actually appending the adjacent here. What I would just have to do is adjacency list of node of nay, adjacency list of node of nay. But now I would be working, right? Yeah. So something like this faster. That's my only thing. Not even. Yeah, it's just not worth it. Okay, no worries. Ignore what I've been doing. Essentially, what I'm trying to do here is we're going to loop through all the neighbors sorted by lexicographical order, right? Because it's like we're going to try whichever one is the smallest lexicographically. If that yields a solution, is like great, like, you know, that'll be lexicographically smallest possible solution done. If not, then, like, you know, backtrack at this point, try the second lexicographically smallest and so on until, like, you know, you try all of them in order and you get some valid solution. And if you don't get a valid solution, it's like, you know, return false. You were too greedy at this point, blah, 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 right? So here's what we'll do. Yeah, for each neighbor's lexicographical order, first of all, if the frequency of that neighbor is 0, that means it's like I can visit this neighbor essentially 0 times right now, right? So it's like, okay, continue, I cannot actually visit that neighbor, right? Otherwise it's like, okay, we're going to quote unquote visit that neighbor, so remove the number of times we can visit it from our current node by 1. Remember, there could be duplicate edges, which is why we're keeping track of these frequencies instead of just the neighbors themselves. So here we'll just do neighbor dict of nay. We're going to minus or equal to 1. Then we're going to add nay to our itinerary. Again, we're visiting this node, so it's like append it to our itinerary and subtracting, you know, from node, we can reach neighbor, you know, 1 less time than what we used to because we're about to use one of the tickets from the current node to that neighbor. Then we're going to try backtracking from this point onwards, and if that returns true, then great, right? Adding this neighbor right now worked, we're solid, and from this point on we'll just return true, so we keep returning true to true and end up using all the backtrack calls. Otherwise, if this returned false, it's like, okay, adding this neighbor right here didn't work. We were too greedy in, like, you know, lexicographic ordering. So it's like, okay, pop that neighbor from the itinerary, add 1 back to, you know, okay, we can use that ticket again from node to neighbor, right? And then loop again through the sorted neighbors to the next, you know, lexicographically smallest neighbor and so on, over and over and over until you either get, like, you know, one point where it's like you have a valid solution. It's like, yay, okay, we find the lexicographically smallest one, and let's just return true and kill all the backtrack calls. Or if we exhaust through this for loop and we never found a valid solution, we're going to return false because it's like, hey, from the current itinerary, you cannot reach any end solutions, end states over here. So that means, like, from a previous backtrack call, you were way too greedy, right? You need to go to another, you know, sort of neighbor and etc., right? And again, like, you know, once we find the very first one, we'll return true and, like, end up killing all the backtrack calls. So once we do that, so once we call backtrack, we'll essentially keep going until we find the first valid solution, which will also happen to be the lexicographically smallest one because we go through them in lexicographically smallest order. And then once we've done that, we just return the itinerary that is, you know, of lexicographically smallest order and valid. And there we go, bada bing, bada boom. We have a working solution to the problem, albeit a little bit inefficient. But there we go. That is pretty much it in terms of how I was able to solve this problem. So that's it from my side in terms of how I was able to solve the problem, although just for my curiosity, because my curiosity will kill me otherwise. Well, first of all, let's check off the fact that we did this problem. Very, very nice. Just for my curiosity, I want to see how NeetCode was able to solve this problem. Now that I solved it, I do not feel guilty. Oh, actually, there's some hints. We can look at the hints. Where airports and those are ticket. Okay, yeah, since we need to use all the tickets exactly once, can you think of an algorithm that visits every edge exactly once? Additionally, how do you insert this lexicograph? Yeah, sure. We build an adjacent list when we give activity, which was that. We perform a DFS to construct the result, but we first sort the neighbors list of each node. Okay, why sorting guarantees? Yep, yeah. Oh, is DFS really just, like, you know, backtracking at the end of the day, as it takes over? Wait. Sure. Where what is that? Brussels sprouts? Yeah. Oh, no. Oh, it's the pan roasted. Yeah, sweet. Where E is the number of tickets, edges, and from V is the number of airports. In this approach, we traverse the graph. We perform DFS. Oh, wait. Yep. And then reasserting it back. Well, can you think of a better way? Perhaps an advanced algorithm that incorporates DFS might be helpful. What? Oh, okay. So Chia-Holzel's algorithm is literally something. Bruh. Okay. We can use Chia-Holzel's algorithm and modify DFS approach instead of appending the node a result list immediately. We first visit all its neighbors. Appending the node. Euler's path. Yeah, I remember Chia-Holzel's algorithm and the Eulerian circuits. I remember this was an easier version of that problem because it's like you were told what to do. Is this the only two? Okay. Yeah, I mean, oh, okay, wait. Okay, default dig for source and sorted tickets backwards. Okay, sure. Okay, some cool thing. I guess Chia-Holzel's algorithm isn't that too complicated, so maybe I should just learn it. Because it's something I know, and I know that it's come up. So yeah, okay, maybe I should learn what Chia-Holzel's algorithm is. We'll stack. So pop a node, DFS from it. Okay, I don't really understand too much what's going on. I remember it's like I tried learning it, I was like, what the heck is going on? It's just, yeah, I'm like, the code looks nice and simple, but yeah, I'd have to learn what the algorithm is and how it actually works. Okay, yeah, I guess this is not, oh, okay, wait, it's literally kind of the same. Source node adjacency, yeah. I guess here he doesn't sort things though, is the nice thing. I guess he sorts the oh, he's abusing the fact that Python dictionaries keep ordering. Okay, that's kind of lame. That's kind of lame. Yeah, Python dictionaries will keep the order. Okay, I don't like that though. It's like you're abusing a property that shouldn't be allowed to abuse, but I get it. Adjacency this, insert. Okay, the backtracking. Oh, thank you, bro. I appreciate you, dog. I'll leave it with you. I'm almost done. No, okay. At least, okay. So there was that's funny. I mentioned Chia-Holzel's algorithm at the beginning of the video. I specifically remember this problem being an easier version of the one that did in the daily problems that required Chia-Holzel's algorithm, and yeah, darn. Maybe I should learn that algorithm on my own time, because this is the second time that algorithm actually comes up in a problem, so maybe it's worth learning. I probably will do this after that video, actually. It's worth learning new algorithms, right? Hopefully, Abdul Bari has a video on it, because that's magical, and I'll learn how the algorithm works. Otherwise, I'll watch a couple YouTube videos on Eulerian circuits and so on. But otherwise, okay, so the first solution is kind of DFSC. The way that I saw him explain it here, removing the neighbor, traversing and reinserting it back. Okay, it's pretty much backtracking. So in terms of DFS and so on, it's the same idea. So I kind of got a similar version of the very first idea. Just maybe his code is a little bit cleaner, probably a lot cleaner than mine, but at least the general concept is the same. And so I'm just happy that I was able to solve the LeetCode hard. So there we go, but makes sense. Chia-Holzel's algorithm and Eulerian circuits. Like Eulerian circuits, I guess that's actually a valid. I should definitely learn that, because there's a lot of problems where it's like you want to visit all the edges, right? And so I should learn algorithms to manipulate problems where it's like you generally want to go through all the edges and do something with it, right? So you know what? I will actually invest time after this video in order to learn that. But otherwise, that's pretty much it for this video. If you did find it useful and enjoyable in any way, shape, or form, I'd highly appreciate if you left a like or comment. But otherwise, I'll catch you next one. So till then, ciao, ciao, my friend. Bye-bye.